that are applicable in this particular chapter. The very first is one that was introduced by a man by the name of Arrhenius. The Arrhenius acid and base definitions are the basics for all other acid and base definitions that we're going to discuss. First half of class today, we'll be working on going through a couple of different, the first 4 or 5 sections of this chapter. Last half of class, we'll be working on a pH lab. In order to get you to the pH lab, one of the things I want you to be able to do is to actually take a pH value and calculate a hydrogen ion concentration, also known as a proton concentration, okay? So that is why we are doing things in this kind of backwards order today. In this particular case, Arrhenius kind of introduces the idea of an acid and says, well, when an acid is dissolved in water, it's going to increase our hydrogen ion concentration. Hydrogen ion concentration just kind of being generic definition. From there, he then says that a base is going to decrease the concentration of hydrogen ions by saying hydroxide ions are the things that are going to increase. So again, the Arrhenius definition is where we start. We will focus most of this chapter on what we call the Bronsted-Lowry definition of an acid and a base, which is one we've discussed before. And then we will finish this chapter off by discussing what a Lewis acid and base are. Okay? Bronsted-Lowry is a much simpler version. We're going to say that an acid is a proton donor and a base is a proton acceptor. So instead of saying that an acid must do this and a base must do this, we now say that an acid and a base both must do something related to protons. Proton donor, proton acceptor. We're going to practice identifying these in balanced chemical equations in this chapter. We're going to practice writing out the K expressions for different acid-base reactions. We're going to talk about how to use the pH scale, also known as the P scale, which is a logarithmic scale that relates the strengths of different things. We can take the pKa, we can look at the pKb, we can look at the pH, which is the most common one you guys have heard of. We can look at pOH, so we can relate the log scale to the concentration of anything, or even to equilibrium constants. This chapter introduces these concepts. Chapter 17 takes them a little further. We talk about titrations. We kind of introduce what they are in this chapter. We won't focus too much on titration science in this chapter. It's something that's going to hit us harder when we get into a future chapter. Okay. All right, so in order for a Bronsted-Lowry acid to be a Bronsted-Lowry acid, there must be an identifiable and removable proton in the species. In order for a Bronsted-Lowry base to be a Bronsted-Lowry base, we basically need to look for a pair of lone pairs, a pair of electrons. So we're looking for lone pair electrons in a Lewis structure on the Bronsted-Lowry base. I'll remind you that when you draw Lewis structures, one atom is typically in the center. You have to fill an outer octet. You're going to put the total number of electrons in there that the different atoms add up to be, et cetera, et cetera. So some of those things from last semester and sophomore year. All right. The next thing we're going to talk about is this whole idea of amphiprotic, a acid or a base. So a species can be both. Up until now, we've kind of said, okay, this thing is an acid, this thing is a base, but there are species out there, one very, very common one that we do a lot of chemistry with, aka water, that are what we call amphiprotic, meaning it can act as either the acid or the base. It can be both. It will depend on what it is placed into or is reacting with as to whether or not it will be the acid or the base. So if you see water in a balanced chemical equation in an acid-base reaction, do not try to say that water is the acid or the base until you identify what the other thing is first. Term amphiprotic just means it can be both. Okay? When an acid dissolves into water. What happens is the proton gets pulled off of the acid and placed onto the oxygen in the water molecule. That species that forms was your daily Q. What's it called? The hydronium ion. Okay? It is called the hydronium ion. Please don't just call it hydronium. It is an ion, meaning it has a charge, boys and girls. It has a positive charge in this particular case. The hydronium ion is a substance that we will assume exists anytime we write a proton into our equations. A lot of times the hydronium ion is written out completely as H3O+. Chemists like to do this thing where instead of writing that out, they just write this. And they assume the presence of the hydronium ion is the same thing as saying, hey, look, protons. This particular reaction, water must act as the base because the thing that's being added to it has a proton on it. HCl acts as the acid in this particular reaction because it has a proton to donate. That proton gets donated and leaves behind a chlorine ion, negatively charged, just like we would have predicted, and then the hydronium species. In acid-base reactions, we always start with an acid and a base as a reactant, and on the right side of our reaction, we form what we call a conjugate acid and a conjugate base. In this particular reaction, the conjugate acid is the thing with the protons, which is what? So look at the right side of the reaction. One of those two things on the right side of your reaction has to be a conjugate acid, and one has to be the conjugate base. If you had to guess, based on the definition of an acid, which one's the conjugate acid? Does Cl have protons to donate? Heck no. So Cl is not the acid, Cl is the base. The hydronium ion is the conjugate acid in this particular reaction. Yes, yes, sir.
How is that though? Like, I don't get how you identify that.
So, on the left side, do you understand that the terms acid and base are applied based on proton donor? Yeah. And then the lone pairs on the water make it the proton acceptor, so it's the base? Okay, well, the same definitions are going to apply to the right side of an acid-base reaction. We're still going to have an acid and we're still going to have a base on the right side of the reaction, but instead of calling them acid and base on the right side, we call them conjugate acid or conjugate base. So the definition of acid and base still apply to the right side. So this guy is a conjugate acid because it has protons to donate, okay? And this must be the base because it's the only other thing present. Yes?
Is hydronium ion, is that amphiprotic or not?
Yes, kind of. I mean, amphiprotic is a term that we usually reserve for species that really exist. The hydronium ion is one that we don't usually do chemistry with. It just kind of is the product of an acid-base reaction. So yes, technically, because it has protons it can donate and it has a lone pair where it could also accept another proton. My answer to you is technically yes.
I'm confused on hydronium and hydrogen. So when you write...
So this is what's really being formed. This is the abbreviation a lot of times.
Okay.
That's all.
That's it.
That's it. They're just interchangeable. Okay, this is what we're talking about. Conjugate acid, conjugate base. The definitions apply on both sides, except that when we talk about the products, we add the word conjugate in front. That's it. Okay? Typically, whatever was the base becomes the conjugate acid. Whatever was the acid becomes the conjugate base. Basic acid-base chemistry. The acid becomes the conjugate base. The base becomes the conjugate acid. Write the whole thing out. Conjugate implies post-reaction. That's all it is. I highly recommend you write the whole thing out and you identify the acid becomes the conjugate base and the base becomes the conjugate acid. In this chapter, we're identifying where protons move, meaning we have to identify where they start and where they end. Proton being H. All right, so let's look at a couple of examples before we move on. Remember to move this. All right. Up here, we want to identify the thing that is not water first, always. The thing that is not water. Does it have a proton?
Yeah.
What does that make it?
Acid.
That makes it the acid. What does that make water in this particular case?
The base.
The base. Acids, by definition, give their protons to bases. So what's one of the things that's going to be formed? Okay. What's the other thing that's going to be formed? Whatever is left over. In this particular case, H is a +1 charge, right? So what's the charge of the thing left over?
Negative.
Thank you. Okay, so acid, base. Now let's identify conjugate acid and base. So what does the acid typically become?
The conjugate base.
The conjugate base. What does the base typically become?
Conjugate acid.
The conjugate acid. Not so bad. All right, let's do a different one. All right. Do you see protons?
No.
So what must it be? Which makes this the? What does an acid do?
Separate protons.
It gives up one proton. So what do we think we're going to start by making?
HCN.
So like HCN. Does it have a charge?
Nope.
No, it does not. What's left over?
OH.
What should the charge on an OH ion be?
Negative.
Okay. Conjugate acid, conjugate base. The acid typically becomes the conjugate base. The base typically becomes the conjugate acid. All right, nice. Moving on. For what we're learning right now, there are no exceptions because we're applying Bronsted-Lowry. We're applying the principles of this particular definition on purpose, and this is so that we can introduce acid-base chemistry before we move on to the next thing. Does that make sense? Okay. When it comes to strength of acids, there are basically two categories here. Strong, weak. Acids and bases fall into strong and weak. If they are not strong, they are by definition weak, and vice versa. Okay? For our particular definitions, when we say that we have a strong acid, what we are saying is complete dissociation occurs in water. That is what a strong acid does. Strong acids typically have weak conjugate bases. So if you start with a strong acid, its conjugate base is weak. Weak acids are only going to partially dissociate. So only some of the weak acid is actually going to give up its protons. Say you put in a mole of your weak acid into water. Only some of that mole is going to dissociate or break apart into the proton and what remains. Okay? Now, since that partial dissociation is a thing, we have a problem. Not all weak bases and weak acids are going to partially dissociate the same. Some of them are going to dissociate maybe 90% of their substance, right, into two parts or more. Some of them might dissociate 50%. Some of them might dissociate 10%. You can see where this gets a little hairy. So we need a scale that defines how well something dissociates and gives us an idea of acid strength. We're going to measure acid strength using the pH scale, as you guys already know. That pH scale is really going to order things based on hydrogen concentration. Yes?
It says like a weak acid that their conjugate bases are weak bases.
Yes.
So the same.
Yes. Yo. Sir.
Do we need to know that generally for almost no charged acids have strong conjugate bases? Or there's something in the book?
Yeah. No.
Or
Yeah. You don't need to worry about it. We're generally just saying strong, weak. Strong means complete dissociation. Weak means partial dissociation. Conjugate bases of both are just weak. That's really all we need to worry about. All right.
yeah.
Yeah. If your thing is not acidic, it's not going to dissociate. It's the definition of not being an acid. If it doesn't dissociate, it's barely an acid. Why we're calling it an acid in the first place is confusing. A lot of times this is because that definition of acid applies in more ways than just proton donor. For our purposes, we're focusing on proton donors as acids. And bases are things with lone pairs that can accept those protons. It's more of a Lewis thing. We're not there. Okay? A lot of times you take this neutral thing. If it does dissociate like an acid in any way, shape, or form, then it forms a pretty strong base. Good call. Predicted the answer. So that was all acid dissociation. Base dissociation is going to be a little bit different. Base dissociation is going to do things kind of opposite. So strong bases will completely dissociate, just like strong acids will. Or strong bases will completely remove that proton, right? They're very good at grabbing protons. Their conjugate acids are typically weak, and so on and so forth. All right. We're going to talk a little bit about the equilibrium version of this. Up here, the thing that's not water, acid or base? Acid, okay? In this particular case, on the left side of the reaction, water is the base, right? And on the right side, chlorine is a base, the conjugate base. In this particular case, since H2O is a strong base, it tends to completely react with the acid that's present, which forces the overall reaction to move towards the products. Okay? So if we had to talk about equilibrium, okay, if we had to talk about that K value, remember that our K values, when they're really, really big, indicate product favored. Yes?
Does this only apply if it's like two elements? Like in the
Acid-base chemistry is typically just one acid plus one base. Yes. What we're saying is that acid-base reaction, set up the way that we're talking about doing an actual acid-base reaction with a strong acid, strong base, kind of strong base, gives us an equation that lies very, very far towards the products. In other words, this is going to happen. We're going to move everything this direction, which means that if we had an equilibrium constant that we could measure, K from last chapter, it would be a very big number. Do you agree that if this is going to fall towards your products, K should be big? Gosh, I hope so. When it comes to a weaker acid, which is our acetate, or acetic acid, sorry. Our acetic acid is going to give up its proton, just like it should, and it's going to form the acetate ion. Acetate ion in this case is a stronger base than our water is. Weak acid dissociates, forms a stronger base than water. Still a weak base, but stronger than water is what we're saying. This means that this particular reaction would lie towards our reactants. So our K should be really small. Just kind of reminding you of some equilibrium chemistry from chapter 15. If K is small, it means things are lying towards the reactant side. If K is big, things lie towards the product side. Okay. That brings us to the very basic acid-base definition of what's going to happen with water. Yes?
So, like, for the previous slide, if it's the side that's weaker, it's going to be favored?
Correct, because the side that has the weaker base has to be produced.
Okay.
Does that make sense? The thing that is stronger is better at pulling the other thing apart. Does that make sense?
Yeah.
So, like, this is good at pulling this proton off to form stuff. Because this is stronger, this thing is going to happen more often to form those things.
Okay.
Does that make sense? It's weird. Really, we're just trying to get you the autoionization equation. Just reminding you of how equilibrium chemistry comes into play. Equilibrium chemistry tells us that one side or another is always going to be favored. It just depends on your reaction. When it comes to acid bases, it's the strength of the actual things that predict which side will be favored. Okay. That brings us to water. So we've said that water can be an acid or a base. We said it depends on what it's connected with, right? In order for us to define if it's an acid or a base. Well, what happens if we put water with water? We can define one molecule as the acid, and we can define one water molecule as the base. Is this what really happens when we put two water molecules together?
No.
Heck no, that would not be great. But for the purposes of the basics behind the pH scale, the autoionization of water, aka what happens if we assume that one water molecule is an acid and one water molecule is a base, is going to be what defines our K value for this particular reaction. It's going to give us the basics on the pH scale. When one acts as the acid, one acts as the base, it forms a conjugate acid and a conjugate base, whatever's left over, just like we did over here. This is one of my products and this is one of my products when I add two water molecules together. What happens if we write a K expression? What would your K expression look like? Anybody want to guess? What would K look like? Capital K. From last chapter. How would you write it? What would you write? products over reactants. Should these be in your K expression? They should not. They're pure liquids. So your K expression should have these products, OH times H3O plus. That gives us this particular expression. Remember that I said a lot of times that chemists will abbreviate this as an H plus. So if you see H plus times OH minus, it's the same idea, and you should have seen that in your reading. This leads us to what we call the ion constant for water. Yes, ma'am.
When it says that's the expression for that process, is that referring to the autoionization?
Yes, that's referring to this reaction.
Okay.
Yes. Okay? The autoionization of water tells us that K at 25 degrees Celsius, aka room temp, should be 1 times 10 to the negative 14th. So is that product or reactant favored? That's reactant favored. That's very reactant favored. AKA, when I said, are 2 water molecules going to form an acid and a base? And you said no. This proves it. This K value says this is not likely to happen. Let's go back to the water molecules. This number is really important. This is why the pH scale goes from 0 to 14, boys and girls. That 14 is coming back for us. Yes, ma'am.
So that KW is constant,
Yep.
not just at 25 degrees, like for anything.
For the most part, we assume everything we do is at 25 degrees, so yeah. We're going to use that for the pH scale. All right. That brings us to the pH scale. Now, some of us have done log-based math before in Algebra 2.
No, recount.
Cool. But you've already done it, right?
Yeah.
The logarithm-based scale in this particular class, this is not natural log. Remember, we've done stuff with natural logs before. This log is always base 10. So this class will always use a base 10 scale. So on your calculator, which I would like all of you to get it out. Just bear with me. Please, please. All I want you to do on your calculator is find the log button. L-O-G, find the log button. You find it? Okay, good. Keep it out. We're not done. Find the log button because you're going to be asked to do logarithm-based math here. Using this particular expression in lab today, you're going to solve for concentrations of hydrogen, or protons, if you will. Remember, this is what you're going to see a lot. This is what I'm going to write a lot. Okay? I'm looking for concentration of protons. That's what I'm looking for. Okay. So, we have this expression. It tells us the concentration of these two things multiplied together gives us the K, 1 times 10 to the negative 14th, right? If I asked you to solve using this information for the concentration of either one, okay, could you do it? You definitely could, okay? You would do this. You'd get the concentration of each one is going to be 1 times 10 to the negative 7th. If they're equal to each other, it basically becomes an x squared situation, equals 1 times 10 to the negative 14th. Take it at face value, okay? The concentration of H3O plus, when they are equal, right? So when the acid equals the base in a situation is going to be 1 times 10 to the negative 7th. Pure water, okay? Talk to me about pure water. It's neutral. I love it. On the pH scale, what is neutral? 7. If you take that 1 times 10 to the negative 7, you plug it into the pH equation, right? So you take that and you put it in here, you're going to get that pH equals 7.
Wow.
Oh, wow. It's funny how math works. Now, remember, we are forcing this onto an arbitrary scale. We are giving this the value. Technically, water will only be a pure 7 pH at 25 degrees Celsius. Right? Because we said Kw was measured at 25 degrees Celsius. It's 1 times 10 to the negative 14th. We said that when they're equal, et cetera, et cetera, et cetera. So temperature does have an effect here. We are, for the most part, going to ignore the effects of temperature for now. We're just looking at what's pH. Okay? All right, on the pH scale, which you guys all know a few things about it at this point, you know it ranges from 0 to 14. You know that values from 7 to 14 are basic. Values below 7 are acidic. When it comes to concentrations of H+, so not just saying that this has a number and it's 1.4, right? Like not just giving it a random number. Concentrations. If your acid has a high concentration of H+, so if that number is big, you're going to have a low pH. If that number is small, you're going to have a high pH. Okay? We're going to do math with this. All right, we're going to look at how to actually use this equation to solve for concentrations or to solve for pHs. The pH side is probably a little easier, right? All you have to do is plug the number in here and plug this into your calculator. But solving for the H+ concentration is a little bit more complicated. How do you do that? Well, this is a log base 10, right?
Yeah.
First thing I'm going to do is try to get that by itself. Remember that a pH is a number between 0 and 14. Okay? Think of it as a variable right now. What do I do next? Well, that's what you did for natural log. What do you do for log with a 10, with a base of 10? We do 10. So 10 to the negative pH is going to equal your concentration of your hydrogen ion concentration. Right? Do this in lab today.
So that's saying whatever the X millimeter is going to be the pH?
Correct. Yeah.
Okay.
So whatever you measure your pH to be, let's say you measure a pH today in lab and it's 4. You're going to take 10 to the negative 4th, and that's going to be your hydrogen ion concentration. Okay. A lot of times our pHs come out to be decimal numbers. In lab today, you're going to have to just give it a whole number because you're going to use pH strips. With our different pH values, okay, we can place many of their different household common substances on there. We're going to measure a few different ones today. We have 14 different things that we're going to measure. We're going to measure everything that is, for the most part, ingestible. Probably shouldn't drink mouthwash or like lemon juice or mineral oil, but like you theoretically you could. We're going to measure a bunch of different things. I think some of them are going to come out to be different than you believe. I've got some shampoo up here. Don't drink the shampoo. For the purposes of this lab, what we're looking for is practice with reading pH strips, practice with calculating ion concentrations, and just kind of learning what are some of the common things that we get or that we are interacting with, right? What are those pHs? All right, the pH scale is not exclusive to hydrogen ion concentrations. We can apply the P idea, so P of something equals negative log of something, to a lot of different things. We can apply it to equilibrium constants. We can apply it to hydroxide ion concentrations. We can apply it to acid dissociation constants and base dissociation constants. When we get to the Henderson-Hasselbalch, there's a lot that we can apply this to. For now, we plug it in and we use one version of the P scale. Not all P scales are going to range from 0 to 14. Okay, this one just kind of happens to be that way because of the autoionization of water. All right. When it comes down to it, pH and pOH are related. Does that make sense? If you think about the autoionization of water, where we said water dissociates into a hydrogen ion and a hydroxide ion, does it make sense that if we take the two and we add them together, we should get the total pH? We go pH plus pOH makes 14. The answer is yes. Yes. In this particular case, it's because of our water constant, ion product constant for water. The takeaway here is if you have pH or you have pOH, you can calculate the other, right? And then if you have pH or pOH, you can calculate concentrations of OH, or you can calculate the concentration of H. This a similar idea with pOH. Okay. You will have some homework problems on doing these mathematical manipulations. So get comfortable with it. Yep. You'll have like 2. You'll be fine. You'll be fine. Yes. Yeah, it won't take you long. Your lab won't take you all of second hour either. You're measuring like 14 things. We'll find out.
14.
Guys, you gotta stick a strip in like some solution. You'll be all right. Oh my gosh.
So we have to do math.
So we're gonna talk about it because I don't have a lot of space for lab today. What we're gonna do is I'm gonna set up like areas where you can go to measure, and then you can go back to your seat and like write stuff down. Does that make sense? Because I don't have a lot of space for you guys to all kind of wander around since I have my projects that are almost done in the back of the room. All right, so measuring pH, what we are going to work with is what we call litmus paper. Litmus paper, for the most part, can, depending on the type of paper, measure pHs from 0 up to 14. Okay, the paper you're going to use is a all scale. But there are different dye papers that you can use that will measure specific ranges. So I have some litmus paper that's actually designed for specifically like blood measurement. So it ranges very, very specifically between 6 and 8, right? And it gives you various shades between 6 and 8 at maybe like 6.2 and 6.4 and 6.8. Just kind of to see where you're actually at on the decimal side of the pH scale. We also have pH meters, and we're going to do a lab later with pH meters. But there are various ways for us to measure pH. One of the easiest is using dyes of a certain kind. And the stuff we're going to use today is dyes that are on paper, and they're disposable. So everything we do today can go down the drain. Everything can go in the garbage. It shouldn't hurt you. It's all stuff literally you can buy at the grocery store. No. You don't. Do you want to? There are something like a ton of different types of indicators. I have an entire cabinet in my back room that's just pH indicators. There are, I would say, probably 200 or 300, right? They range for different purposes in different solutions. Think if you're using a certain kind of acid, it could maybe not react or bind to the dye, so you can't use that particular dye, you have to use a different dye. We'll talk more in depth about dyes in a little while, because we'll be using dyes when we do titrations. Okay? The other very accurate measurement tool that we have is actually a pH meter. The pH meters are pretty sensitive in this particular class. They are electronic and they are lab pro ones, so you'll have to use your lab pros. They have these ion sensitive membranes that like to dry out, so you have to be pretty careful with them. They're little glass bulbs, and they can break pretty easily, so when we use them, you're going to be careful. That is where I think I'm going to stop. Go ahead and get your lab open. Yeah, that's what I'm saying. It's on Canvas. It is not something you have to do in your notebook. It is a download and do. So get the file downloaded on your computer. Start reading about what you're going to be doing. I will ask that you work with a partner.
Who does that? I don't know. I don't know if I can name a single person that doesn't love it.
I see that you have two pH things on the table. Do you want us to take an average if we get two different
So
ones?
I want you to take 2 pHs.
Alright, but
Like you and your partner, each one of you take it.
oh,
and
then
read it?
do you want us to average it if it's not the same?
Yeah, that's the. I mean, I want you to write them both down, and then
Yeah.
we'll take your average after. Good question.
How many liquids do you have?
14.
Just look at the table, you can figure it out. Yeah, figure it out.
I didn't look at it, but I know how it goes. It's not physics, is it?
Hold up, hold up. Don't move. Okay, what? Which is fine. What you get? What?
Well, he was like, how many hours do you work on? And I was like,
Really? She hasn't been talking about it. I think her prediction might, she might be going to.
All right, boys and girls, listen up. When you're doing this, each of your lab partners needs to take a pH. That's why there's 2 columns for pH. You're going to average the 2 readings. One of you may read something at a 7, one of you may read something at an 8, average is 7.5. Make sense? You are going to interpret all 14 on your own, and then you will go to and sit with your partner and add the 2 together, record an average. Does that make sense? Yes.
Where do we write them two
If you have
opposite of
3,
each, so
just
I'll
make
do
sure
it.
that each one gets taken at least twice.
Yes.
You can take it 3 times and take the average of 3. I mean, that would be even more accurate. I would say that's actually better, personally. So make sure yours get written down in the first column, and then do your average in the second column.
No.
Does that make sense? Yours right in the first column, get the average written in the second column after all of them have been taken. All right, so here's how we're going to do this. You're going to have a group number. Please move yourselves to your, are you guys working together? Yeah. And you guys working together? Okay. And then you're working separate? Okay, so you're going to be groups 1, 2, and 3. 4, 5. 5. You're working with? You're working with Carly, okay. So you and Carly.
Wait, I was working with Molly.
Okay, fine.
I thought autoionization would be that part.
Just whatever, it's fine. So why don't you and Ben work together? So you're gonna be group 6. Molly and Carly are group 7. Shelby? You guys are group 8. You 2 are gonna be group 9. Okay? Alright, so groups 1, 2, and 3. I'd like you back at those 2 tables working on your pHs. Groups 4 and 5 work at this table over here real fast. Group 6 over here. Okay? The rest of you just kind of hold off for a second. You just need to take, so these are your pH strips, all right? You're going to go ahead and you're going to dip your pH strips into the solutions, and you're going to record what you see. There's a chart on these little vials. Make sure you use it. It'll help you decide what the pHs are. Okay, so can you shake those before you pour them out over there? I'm still working on it. Yeah, so
It doesn't depend on how you put it.
you just stick it in. Yep. Alright, so we want to get now. We want it to be like. We just want it a little bit. Okay, so we want to try to not see the pink. Yeah. I would say most of them. What do we do with all the leftover pH? If you use them, they go in the garbage.
Just a best guess.
I'm worried about those ones. Huh?
Do I have to go by point or by phone number?
Pull number.
Yeah, so the stick turned green, but it's turning blue.
Oh, that's because of the white. Hey guys, try to like wipe them onto the like side so that you actually can see the color. Okay? Your goal is to just get the strip itself wet to see the color. Once you see the color, you can put it off to the side.
Divided by 3.
Divided by 3, so 4.
So that's 13 divided by 2.
I
I got 10 for this. But you guys have their own voice. No, average was 4.3.
Wait, average of what?
4.3.
No, it's not.
Yeah.
Okay.
You're a little pessimistic.
I knew that was going to
Don't do that yet.
Average was 4.3. What's the blue stuff over
It's in an annex.
Which,
It's a really like intensive.
President.
well, it's a base, because it takes
All right, you finish at your stations. Please go ahead and take a seat again. I'm gonna move my next groups in. What are you, 7, 8, 9? Group 7, you can go ahead and work on the whoever group 7
I'm not done working.
in the middle of God.
I'm in the middle.
I got it,
Would you get, 9
5, 5, 5. So 9